Hello, this is section 6.4 in your textbook. It's about conditional probabilities. So this video is for all of my quarantined and e-learners out there. So today we're going to talk about conditional probability. And the idea of conditional probability is that there's some condition, something that happens that makes you know more than you did before, and it changes the probability sometimes. So for example, let's say that I have two dice, and I'm going to toss them, I'm going to record the sum. And I want to know what's the probability that the sum is less than 10. Sum is less than 10. So I think about my sample space here, and I have all of my sums that there are 36 possible outcomes there, and sums less than 10. It's actually easier to count the ones you don't want. So there's 1, 2, 3, 4, 5, 6 that are greater than 10. So that gives me 30 out of 36, or about 0.833, that are less than 10. All right, so what's the probability that the sum is less than 10? About 83%. Now, let's say that I throw the dice, but before I record my sum, my friend says, hey, you got doubles, cool. All right, so I know something now. If I want to know what's the probability that I got a sum less than 10, I'm not looking at all 36 outcomes anymore because my friend let it slip that I know that it is one of the doubles. So my sample space has gone from being 36 outcomes down to 6. Now I know I'm just talking about the doubles, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. And so of those, there are 4 possibilities that are less than 10. So my probability now of getting a sum less than 10, given that I know I wrote doubles, is 4 out of 6, or 0.667. So the probability has actually changed because I knew something, or I know something. And so this is the idea of a conditional probability. I'm not talking about the entire sample space. I am looking at a smaller sample space than this. My sample space has been reduced because now I know more information than I had the last time. All right, so there is a formula for conditional probability, and it is on your formula sheet. This is not something you have to have memorized. And so what you're going to see on your formula sheet is this formula, the probability of A, and it's got this little slash right there. That little slash, you would read that as the word given. Okay, the probability that event A will happen given that event B has already occurred is called a conditional probability. And we would find that by taking the probability of A and B, remember that intersection symbol that means A, divided by the probability of B. Or in other words, instead of looking at the whole sample space, we're only looking at the B's, only the things that we know, and we want to know how many of the B's are also A's. Okay, so in our problem, the way this would look like is if I wanted to know what's the probability that I have a sum less than 10, ooh, that handwriting of mine, given that I know that I rolled doubles. Okay, so if I wanted to do this with a formula, I would say, okay, that's the probability that the sum is less than 10 and it's a double. That's 4 out of the 36. Okay, because there's 4 doubles that are less than 10 out of the whole 36, divided by the probability that I get doubles. There are 6 doubles out of the 36. 4 out of 36 divided by 6 out of 36. If you were to imagine dividing and multiplying by the reciprocal and canceling out, that leaves us with that same 4 out of 6 when we did it through logic and reasoning there. Okay, so the idea with the conditional probability formula is that if there's no way to kind of reason it out, if you know these two features, you can put them into the formula to solve. So let's see what that looks like on the next page. All right, so I have a problem that says you survey a sample of high school seniors and determine that 75 are taking a math class. Sorry, got too far down there. 80% are taking an English class and 60% are taking an English and math class. If a student is selected at random, find the following probabilities. So the first question says, what's the probability of not taking a math class? Okay, so that's a complement. We talked about that yesterday. So the complement's the opposite. So I know that if the math is 75%, because the problem prompt told me, that not taking will be 1 minus 0.75, which is 0.25. That's my probability. And remember, you want to show that subtraction step in the complement, even though you could probably do that in your head. Show that step, okay? Make those AP graders happy that you understand how complements work. All right. The next question says, what's the probability that they're in a math class given that they are taking an English class? So the first thing I would suggest is always write that conditional statement in context and show the substitution into that. So for example, we're going to say, what's the probability of math given that we know that they're taking English? So remember, our formula is A and B on top, so that would be math and English in the numerator, divided by the probability of B in the denominator. That's the probability of English. So out of the people taking English, how many are also taking math? Now, I don't have a table to look this up. I don't have a way to count this, but I do have up here in the problem prompt, it says 60% are taking math and English. So that gives me a 60% in my numerator here. And 80% are taking just English. So 0.60 out of 0.80. And if I put that in my calculator, I end up with 0.75. So the probability that someone is taking math, given that you know they're taking English, is 75%. Okay? Now, a little quick note here. Do you notice that the math is 75% and math given English is also 75%? In the next lesson about independence, we're going to show that since though English didn't change the probability of math, that those two things are independent. So, spoilers. Now, the other question says, what's the probability that a student taking a math class is taking an English class? This one's worded kind of weird. It doesn't say exactly the word given, but it does, because it doesn't say a student is taking math and English. What it says is a student taking a math class. What kind of student? One of our math class students. So that is known, that is given. We know that they're taking a math class. So what's the probability that one of these math class kids is taking an English class? So the reduced sample space, it's not all students anymore, it's math class students. So that's going to be our given. So this time it's the other way around. What's the probability they're taking English given that I know that they're taking a math class? Now the numerator will still be the same. It's the intersection, math and English, which is still 60%. Okay. But now the thing I know is that they're taking math, and that is 70%. And 60 divided by 0.75, that is 80%. Okay, so notice that the direction does matter. Okay, the order matters in this. The thing that's given is your reduced sample space. Okay, all right, so let's take a little frequency table here. So it says, you record the results of what food and what drink individuals order from the concession stand. If you select one customer at random, find the following probabilities. All right, so here goes. What is the probability that someone likes a hot dog? Okay, now notice that we're selecting one customer at random. There's nothing special about this. This is just like yesterday. So out of our 400 customers, it looks like there's 158 who like hot dogs. And pizza, I look up pizza here. There's 182 out of the 400 that like pizza. Hot dog or pizza. Okay, so I know that there are 158 who like hot dogs, and there are 182 who like pizza, but there's no overlap in this. So I don't need to worry about counting anything twice. So I just put my 158 and my 182 together, and that's going to give me 340 out of the 400. All right, pizza and hot dog. Now I see that word and, which means I'm looking for the overlap. I want to know where pizza and hot dogs overlap, and it looks like they never do. So if there's no overlap, it must mean that those two are mutually exclusive, they're disjoint, and they have a probability of 0 because there's no overlap there. Pizza and water, I look at my table here. Pizza and water do overlap. They overlap 58 out of 400 times. And then finally, pizza or water. So again, this is one of those ors, so we have to be careful. Pizza is 182 and water is 140, but they are overlapping at that 58, which means the 58 is counting in the 182 and it's counting in the 140. So I want to do 182 and 140, but I need to take off one of the 58s so it's not counting twice. Another way to think about this is you want all of the waters, all 140 waters, but you need to add on the 120 pizzas that got soda and the 4 pizzas that had no drink. Either way, you are going to end up with 264 out of 400 for that probability. Okay, I had to move my table down so we could see the rest of this. The next question says, what's the probability that they ordered soda given that they ordered a hot dog? All right, so I'm going to translate that into symbols here. What is the probability that they ordered a soda given that they ordered a hot dog? All right, so the way you want to think about this in terms of condition, I don't really want to use the formula for this. Instead, I want to think about this in terms of a reduced sample space. If I know, if it's given that they ordered a hot dog, what that means is that I am literally only looking at the data from the table where the person ordered a hot dog. So I am not looking at all 400 people anymore. I am only looking at the 400 people who ordered, sorry, at the 158 people who ordered a hot dog. So out of the 158, not out of the 400 this time, out of those who also ordered soda, that would be 50. Okay, I'm going to switch colors here. All right. What about the next one? What's the probability that they ordered no food given that they ordered a soda? So again, this time it's given that they ordered a soda. That means I'm not looking at all 400 people anymore. I know that they ordered a soda. So I'm only concerned with those 200 people in the soda category here. So I'm going to say given soda, 200 people. So out of those sodas, how many people didn't order anything? That would be 30. 30 ordered no food out of the soda. Okay. The next one says a customer who ordered water also ordered a hot dog. All right, so again, it's not just any old customer. It's a customer who ordered water. So I want to be careful then. Okay, I want to be super careful because it says a customer who ordered water. That's what I know. That is what is given. Also ordered a hot dog. So it doesn't say a customer ordered water and a hot dog. It says a customer who ordered water. That's the kind of customer it is. So that's what's given. So when I write my condition, I need to put water there as the given condition, and the hot dog is the thing we're looking for the probability of. So I'm going to go up here. If I know they ordered water, then I'm only looking at the 140 people who ordered water. And out of those 140 people who ordered water, it looks like 62 ordered a hot dog out of that category. Okay? And then finally, a no food customer. A no food customer. I made these problems up, so some of them are kind of dumb. Sorry. A no food customer ordered water. So again, it's not a customer ordered no food and water. It's a no food customer. That's the kind of customer it is. That's what's given. That's what's known. Okay, so we know they ordered no food. We're going to write that as our given. And then we ordered water out of those. So I'm going to look at all the people who didn't order any food at all. So I'm only looking at those. I'm not looking at all 400 anymore. I'm just looking at the 60 that didn't order any food. Okay, out of those, it looks like 20 ordered water. So my probability here is 20 over 60, which is going to be about 0.333. Okay, so with a conditional probability from a table, when you know the given, instead of taking your answer out of all 400, you're going to take your answer out of the reduced sample space. So here's another one. It says you randomly choose a survey participant, okay, from this table. What is the probability that someone is greater than or equal to 50 years old given that they answered once a week or less than once a week? Right, so this time once a week and less than once a week, that is what's given, that's what's known. So it's not just one column in the column, it's just like the whole thing. Like, so I need all of the once of the weeks and all of the less of the once of the weeks. So what we think here is that if I add these up, there are 207 people who said once a week, and there are 384 who said less than once a week. So a grand total of 591 people sort of in that box. So as for the denominator, out of the 591 people, just in that orange box, just the once a week or less than once a week people, how many were greater than 50? So it looks like there were 69 who said once a week, and there were 126 that said less than once a week in that greater than 50 category. So I'm going to put those two numbers together out of my 591. All right, and that gives me 195 out of 591. All right. Now, when we're talking about conditional probability, one of the reasons why we need conditional probability is because we want to be able to use the multiplication rule for probabilities. All right, so the multiplication rule for probabilities and the multiplication rule for events is kind of along the lines of the same kind of problem you would have worked back in Algebra 2 when they said Bob has 2 pairs of shorts and 3 pants. How many outfits can he make? So the idea is when you're doing multiple things, choice 1 times choice 2 gives you the combination of both choices. Okay, so the multiplication rule for probability says that events A and B will occur is equal to the probability of A multiplied by the probability of B given that A has already happened. Okay, so that's where that conditional probability comes into play. Another way to think about this is if you wanted the probability of A and B, you're going to multiply those two events together, multiply those two probabilities together. But you need to be careful because the second time, the first one's already happened. So just be cautious for this. Now, most of the time this comes up if you've got independent events, which we're going to talk about more in the next section. What's the probability, for example, that you guess correctly 4 times in a row on a true and false test? So, assuming this is totally random and they're not connected to each other in any way, the probability of being correct is 50%, 0.5. So doing it 4 times in a row would be 0.5 times 0.5 times 0.5 times 0.5, or 0.5 to the 4th, which is 0.0625. Okay, so if there's a 70% chance that I'm going to guess correctly on something, there's a 0.7 times 0.7 times 0.7 times 0.7 that I would guess 4 times in a row. Or if there's only a 25% chance that I'm going to guess correctly, there's 0.25 times 0.25 times 0.25 times 0.25 times in a row. Okay, so we just would repeat those probabilities using that multiplication rule. All right, now let's suppose I am drawing a card from a deck of cards. Okay, and it's a standard deck of 52 cards. And from the first deck of cards, it says, what's the probability that both cards will be hearts? And we're doing this with replacement. All right, so what this looks like in terms of probability, I'm going to draw 2 cards. And I want to know what's the probability the first card's a heart? Well, that's 13 out of 52. Okay, 13 hearts out of 52 total cards. Then times the probability that a second card is a heart, given that you know the first one is. Now, the fact that we put it back means that the deck hasn't changed. So the second time you draw the card, there's still a 13 out of 52 chance of getting that card. So I'm going to take in my calculator, 13 out of 52 times 13 out of 52. That's 0.0625. Now, if you take your 2 cards again, but this time you do it without replacement, the probability that the first card is a heart, still 13 out of 52. But when you don't put it back, the probability that the second card is a heart, if you got a heart the first time, given that you've already gotten a heart, that has reduced down to 12 out of 51. There's 1 less total card and there's 1 less card. Put that in your calculator, you end up with 0.059. And just to kind of point this out, this is why I'm saying you should always round to at least 3 decimal places, if not more. If we were to round these 2 probabilities to 2 decimal places, they would both come up to 0.06. And that wouldn't really allow us to see the difference between the 2. So at least 3 decimal places will help us see the difference between some more subtle probabilities. Okay, all right, so let's move on. What are we going to do? So we know with multiple events, we can multiply the events. So I have this question. This is a very common style of question, so we're going to talk about these over and over and over again. Suppose you know that 60% of Avon High School teachers are females and 45% of the females teachers have a master's degree or higher. Of the male teachers, 55% have a master's degree or higher. So to do this, anytime you start seeing percentages of percentages, instead of making a table like we did yesterday right away using raw counts, when you're doing percentages of a percentage, the way you want to start is by drawing a tree diagram. So let's get this started. So I know that we've got females and males, and I know we have teachers with master's degrees and not master's degrees. So when I look at the master's degree, it says of the males and of the females. So that means that's going to be the second branch. So we're going to start with our tree diagram. We're going to start off with females. It says females are, there's 45% of Avon High School teachers are females. So I'm going to put 45. Okay. And then that would mean that the rest of that 100%, that complement, would be males. All right, so if 45% are female, that would mean that the rest of that 100% are males. That's going to be, oh, and I read the wrong one. Oh, how embarrassing. Let me get my little eraser out. Eraser of shame. Here we go. Let me try again. Let's see if I can read this time. 60% of Avon high school teachers are female. How about that? So I'm going to make 60% female. And so the complement now would be 40% of them are male. Ah, there we go. All right. So 60% are female, which means the other branch, they have to add up to 100%. That is going to be 40%. So now it says 45% of the females have a master's degree. So I'm going to go ahead and say master's, and that is 45%. So that means that the group that does not have the master's, that would add up to 100%. So if 45 of the females do, then 55% of the females do not. Okay? I'm going to do the same thing down here with the men. 55% have a master's degree or higher. So I'm going to go up master's. Completely made up these numbers for the problem, so I'm not trying to point out anything or talk about any of that business. We don't really know. I just totally made these up. So that would mean the not would be the rest of that. So if 55% of the men do have a master's, then 45% do not. Now, you can probably solve many of these questions without doing this, but I strongly recommend you're going to take these numbers and you're going to turn them into a table. All right, so what you want to think is your first split gave you females and males. That's the first split. So I'm going to put that on the side of my table, and I'm going to say we have females and males, and then you always are going to want to add a column or a row that says total. Total is very important. It implies that you did addition to find your answers, which can sometimes count as work. Okay? And then the other choice was masters and not a master's. So I'm just going to put masters and not and total. Okay, so my first split was females and males. My second split was masters and non-masters. Okay, so, and then at the end, since these are percentages, the total should add up to 100%. Okay, so what we're going to do then is to find the number that goes in this box right here, this first box. This is where females and masters, that's where they would cross. That's the intersection. To find that, I'm going to multiply down the branch of the tree. Multiply down the branch of the tree. And you're going to want to actually write that multiplication down somewhere. You want to show that product because that's going to show as work. I like to put it right here at the top of the table, but you could also show it out to the side of your tree. So I'm going to go 0.6 times 0.45. Okay? And multiply down that branch of the tree. And then inside that box, I'm going to write what that product is. So I'm going to take 0.6 times 0.05 or 0.45, and that gives me 27%. Okay, so that multiplies. So 27% is the intersection. That is out of the whole school, the percentage of people who are female and have a master's degree. And I'm going to go ahead and do this with the rest of those. I'm going to multiply down the branch. So to find females and not, I'm going to multiply down that branch of the tree. I'm going to write that product. That's 0.6. Sorry, my pen didn't change here. Okay. Got it. 0.6 times 0.55 this time. Right? And then for males and master's degree, I'm going to multiply down that branch of the tree. That would be 40% times 0.55. And then males and not master's degree, I'm going to multiply down that side of the branch. That's 40% times 0.45. All right, and once I have these products, I can actually multiply here. So 0.6 times 0.55, that gives me 0.33. And when I put these together, you're going to notice there's my 60% female. 0.27 plus 0.33 gives me that 60% female. I'm going to do the same thing here. 0.4 times 0.45, that is 0.22. Okay, 0.4 times 0.45, that is 0.18. and I can add up, and there's that 40%. But now what I've figured out is I can also add down now and get the percentage of the whole school that has a master's degree. So when I add down here, I can see that 49% have a master's degree, and also that means that 51 do not. Okay, so by converting this converting this tree diagram over to a table, we're able to answer some really easy questions. Before, they weren't necessarily easy. What is the probability that a teacher has a master's degree or higher? I can look at my table and read that right off the table. That is 49%. Okay. I could also, what is the probability that someone is a female given that you know she has a master's degree? Okay, so now if it's given that she has a master's degree, I know I'm only looking at that portion of my table right there. So of the people who have a master's degree, of the 49% of the group that has a master's degree, 27 of that 49% are female, and that tells me that the percentage is 0.551. Okay. All right, now, without this table, you're going to have to actually write down the work in order to get full credit, which would mean you would have to find all these individual products and show the work to get there. The table is how you want to do this. You want to show the multiplication, you want to show the addition, you want to make sure you have that word total, and that'll take care of this and make this a much easier problem than it's going to be otherwise. And make sure you grab all those points because you want to get a 5. 4 out of 4 on the question, 5 on the exam. Okay? All right, so conditional probability. If you're looking at a table, you don't need the formula. Just chunk out your section of the sample space that you want, and then do the portion of that sample space. It's literally, when I say like given master's degree, it's like I'm only giving you the information that deals with master's degree. Okay, if you don't have a table to read, maybe you can make a tree diagram with your percentages and turn it into a table. That makes answering these kinds of questions really easy. Or if you don't have a table and you can't make a tree, it's possible that you might be able to figure out and use that formula in order to figure out that conditional probability. All right, thank you so much.